This is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are discussing problems based on LMTD and NTU methods in a heat and mass transfer subject. In heat exchanger, the amount of heat energy that is extracted from the hot fluid to the cold fluid only because of thermal protection difference which is existing between the two fluids when it is flowing along the length of the pipes. Here the equation which is used for determining the quantity of heat energy flows is given by Q is equal to UA TH minus TJ. That is the amount of heat energy that is transferred. It is based on the temperature difference between the two fluids and surface area, and U is representing overall heat transfer coefficient. But here the TH and TC, the difference of the temperature of two fluids, is not the constant entire its length when it is flowing. When the two fluids are moving in parallel to each other, that means the hot fluid is entering here now. If I take that is, this is the length of the pipe now, the temperature. The hot fluid is having higher temperature, it is there. While moving along the length, the temperature decreases. But cold it is there now, that is a cold fluid which is having lower temperature. When it is moving around it now, it goes, temperature increases. That is when it is here existing now, the temperature of the hot fluid is decreases, the temperature of the cold fluid is increases now. Here TH minus TC is representing the temperature difference between the hot fluid and the cold fluid, but it is not the same entire its length. Hence, it can be represented as Q is equal to UA into delta T M now, where delta T M is the here mean temperature difference. Here in these terms, U is representing the overall heat transfer coefficient. Generally, it is measured in watts per meter square per degree Kelvin. And A is representing the area of the cross section, which is represented in a meter square. And the delta Tm is representing the mean temperature difference. Sometimes it is also called logarithmic temperature difference, which is measured in degree of Kelvin. Okay, heat transfer through the wall. If you take here now, wall is there. Here one side is having this higher temperature fluid, other side is having lower temperature fluid is there. The heat energy is flowing from higher temperature fluid, which is having, it is not through the wall. Again, it is a transfer to the fluid which is the adjacent to the wall, which is maintaining at lower temperature. Okay, in this process, first of all, the heat energy is flowing from the hot fluid to the surface of the block, that's the wall what we are calling now, by using convection process. And heat energy flows from the one side of the wall to other wall, that is within the wall, is by using conduction process. From the wall to the again cold fluid by using convection process. Since the heat flow is in steady state condition, that is the amount of heat energy flowing per minute remains constant now. Hence, it can be represented as here now. Within the wall, it can be represented as Q is equal to Ka into N now, Ts1 minus Ts2 divided by delta now. From this one, we can take it as delta Q into delta, this delta is there, it is called here thickness, divided by Ka is equal to Ts1 minus Ts2. where Ts1 is representing the temperature of the wall at the inlet, that is which is having in contact with the hot fluid, and Ts2 is representing the temperature of the surface which is having in contact with the cold fluid. Similarly, the amount of heat transfer from hot fluid is given by H0 into A into here Ts1 minus Tc. This is nothing but it is equal to here now from H0, it is the temperature of hot fluid to the wall is given. From this relation we got Q is equal to H0 A into Ts2 minus Tc now. Similarly, from the here we are having from hot fluid to the surface is given by Q is equal to H0 A into here THO, that is the temperature of hot fluid, minus Ts1 now. Similarly, from the fluid, from the wall to the cold fluid is given by Q is equal to Hc into A into Ts2 minus Tc, where Ts2 represents the temperature of the wall which is having in contact with the cold fluid. Since Q is a constant now, adding this left hand and right hand side separately, toward the right side we are having here the equations Ts1 minus Ts2 like this, Ts1 minus Tc and so on now. Adding all these things, so finally we are having Th minus Tc, it is there, that is which is equal to Q into 1 by Hia plus delta Ka plus 1 by H0 Ea now, where Hi and H0 are representing the coefficient of heat transfer by using convective mode from the hot fluid to the wall, similarly from the wall to the cold fluid, where K is representing the thermal conductivity of the wall, A the area of the cross section, assume it is the constant for the entire process. So, this equation it can be represented as now Q is equal to Th minus Tc divided by, is the reciprocal of this values we are taking now, that is 1 by Hia plus delta by Ka plus 1 by H0 A now. This 1 by Hia, it is called thermal resistance by the conduction process from a wall to the cold fluid. Delta by Ka is representing the thermal resistance of wall, it is called conduction heat resistance now. 1 by H0 A is called convection heat resistance for the hot fluid to the wall now. Just combinedly it can be represented as Q is equal to Ua into Th minus Tc. Here logarithmic mean temperature difference is there now. That is the amount of heat energy that is flowing from hot fluid to the cold fluid. It mainly depends upon the temperature difference between the two fluids now, as well as the surface area which is separating hot and cold fluid. And H0 is nothing but representing that is the heat transfer coefficient for the convection process. In a parallel heat exchanger process, the two fluids are flowing in the same directions. That means if I just here according to this graph now, here Ts1 Tci is representing the temperature of the cold fluid at the inlet. It is very, very low. Its value is increasing just when it is moving toward the right side. Here Ts2Co is representing the temperature of cold fluid at the outlet now. Similarly, Thi is representing the temperature of hot fluid at the inlet. This value gradually decreases. Finally, it is having Tho at the outlet of the heat exchangers. So, if we observe, there is a maximum heat temperature difference there at the inlet of the exchanger and minimum value there at the outlet now. That means the temperature difference is not constant entire its length now, in the case of parallel flow heat exchangers. In counterflow exchangers now, assume just here now, hot fluid is having temperature Thi at the inlet. Assume it is moving toward the left side, right side positions, while leaving its values having Tho, that is the temperature of hot fluid at the outlet. Similarly, the temperature of the cold fluid at the inlet is a Tci. It is moving, that liquid is flowing from the right hand side to the left hand side. That is, it is called a counterflow direction. That means these two fluids are flowing in opposite directions. So, by leaving the temperature is Tco, that is the temperature of the cold fluid at the outlet position. It is inlet, this position is representing outlet position. The difference of these two temperatures is almost constant when they are moving parallel to each other now, but in a counter flow now. So that's why we are taking here now delta Tm is representing the mean temperature difference, which is used to find the amount of heat energy that is flowing from hot fluid to the cold fluid. So the final equation is the amount of heat energy that is flowing. It can be determined as Q is equal to U into A delta T0 now, that is representing the temperature difference of two fluids at the outlet, minus delta Ti, the temperature difference at the inlet, divided by log of delta T0 divided by delta Ti now. This value is called now logarithmic mean temperature difference. So by using these equations, we can determine the magnitude of heat energy that is flowing in a pipe, that is in heat exchangers now. Okay, these are the certain problems we are discussing based on this formula. Determine the area required in parallel flow heat exchanger to cool oil from 60 degrees centigrade to 30 degrees centigrade using water available at 20 degrees centigrade. The outlet temperature of the water is 26 degrees centigrade. The rate of flow of oil is 10 kg per second. The specific heat of the oil is 2200 joules per kg per degree Kelvin. The overall heat transfer coefficient is U is equal to 300 watts per meter square per degree Kelvin. Compare the area required for counterflow exchanger also. Okay, the first data is related to the two fluids, that is hot fluid as well as the cold fluid, both are moving in the same directions now. That is, according to this figure, they are moving from left to right side position now. Okay, just drawing an ear diagram now, which is representing the x-axis is representing length of the exchangers now. That y-axis is representing the temperature of fluids at the inlet as well as the outlet of the exchangers now. So for hot fluids, the inlet temperature is equal to 60 degrees centigrade given, and cooling to 30 degrees centigrade like this now, when they are moving from left to right position. At the same time, for the cold fluid, it is having temperature 20 degrees centigrade at the inlet and 26 degrees centigrade at the outlet. That is, maximum temperature difference is there at the inlet. That is, the temperature difference is equal to 60 minus 20 at the inlet to 30 minus 26, that is 4 degrees centigrade at the outlet position. So Q is equal to, according to the problems, mH into CH, TH minus THO, that is the amount of heat energy that is extracted from the hot fluid, which is equal to mH is equal to here given, here 10 kg oil that is given now. Specific here it is given 2200 joules per kg per degree Kelvin is given. Here the temperature difference 60 minus 30, Even though if you mention in Kelvin or the centigrades, the effect of this values will not change. Hence, I kept as it is only 60 minus 30, which is equal to here 6,60,000 watts. This is the amount of heat energy that is extracted from the hot fluid to the, that is fluid, hot fluid, when it is flowing from left to right directions. That is, its temperature decreases from 60 to 30 degrees centigrade. So Q is equal to UA into LMTD, that is the logarithmic mean temperature difference, which is equal to, we are taking 40 minus 4, that is the delta I, divided by log in is given now. That is, here the difference is 40, that is the delta here T at inlet minus delta T at the outlet is given. That is, this value is equal to 40, this value is equal to here 4 now, 30 minus 26. So this is the difference of these two values divided by log of 40 divided by 4, which is equal to 15.635 degrees centigrade now. So by substituting these values in this equation, Q is equal to, already we got UA into LMTD. Here from this relation we got Q is equal to 6,60,000, which is equal to, here the overall coefficient of heat transfer coefficient is given 300 watts per meter square per degree Kelvin. From this one we got 300. We have to determine these values into 15.635, that is the temperature. From this we got the area, the surface area which is required is equal to 140.71 meter square now. For the counter flow directions, that is the two fluids are moving in opposite directions. Okay, according to this problems we are taking now. Here the 60 degrees is representing the inlet temperature of the hot fluid. It is flowing here towards toward the right hand side. The final temperature is equal to here 30 degrees centigrade. Similarly, for the cold fluid, it is having 20 degrees centigrade here now. The finally the value is equal to 26 degrees centigrade now. Here from this relations we got the temperature at the inlet is equal to 60 minus 26 is equal to 34. At the outlet is equal to 30 minus 20 is given, which is equal to 10 no, divided by log of 34 by 10 no. By using this equation we got LMTD is equal to 19.611 degree centigrade. So substituting the values here from this equations we got, that is Q is equal to, arrange the equations now, that is H into A into here T hot fluid minus T H I. By using the equations already we determined these values now, which is equal to, in previous case we determined it is equal to 6,60,000 watts now. By substituting these values in the equations now, that is Q is equal to Q into A into delta T M. From this relationship we got A is equal to 112, that is 112.18 meter square now. That is on comparing these two areas, that 20% of surface area less is required in the case of counterflow heat exchangers in order to reduce the temperature of hot fluid from 60 to 30 degrees centigrade, or in order to increase the cold fluid temperature from 20 to 26 degrees centigrade. Okay, the flow rate of water can also be determined as it will be required. From this data we got Q is equal to MCCC TCO minus TCM. That is where MC is nothing but representing the mass of the water that is required, that is cold water. CC is representing specific heat now. TCO is representing the temperature at the outlet minus TCA. This is the amount of extracted by the cold fluid. By using these equations, we got MC is equal to 26.32 kg per second. This is the flow. The counterflow arrangement provides more uniform temperature difference along the flow and hence better rate of heat flow that can be obtained. And moreover, it is mostly preferable for the engineering applications. The counterflow type is also used to cool the or heat over a wide range of temperatures. These are the two advantages of using the counterflow for construction of heat exchangers. Okay, determine the area required for a shell and a tube exchanger with the two tubes passes to cool oil at the rate of 10 kg per second from 60 degrees to 30 degrees centigrade, flowing in the shell using water at 20 degrees centigrade, passing through the tubes and heated up to 26 degrees centigrade. The specific heat of the oil is 2200 joules per kg per Kelvin. The value of overall heat transfer coefficient is 300 watts per meter square per degree Kelvin. Here we require to determine the area required for the shell and tube heat exchangers. The heat flow rate is given by the equations now. Q is equal to mHCH delta TH. This is called here now. In other words, the amount of heat energy that is extracted from the hot fluid, which is equal to here mass of the fluid is given, oil is given 10 kg per second, 10. The specific heat of hot fluid is equal to 2200. The temperature difference is equal to 60 minus 30. From this relation, we got 6,60,000 watts now. LMTD for the counterflow directions now is given 60 minus 26. Here it is given. That is a delta T at inlet. That is a 60 minus 26. At the outlet 30 minus 10. Sorry, here 20. Here is it 10 degrees is given now. So on substituting these values, we got 19.611 degrees centigrade. Okay, P equal to now here 26 minus 20 divided by 60 minus 20, which is equal to 6 by 40 or 0.15 now. R is equal to 60 minus 30 divided by 26 minus 20, which is equal to 5 now. So reading from the chart, we observe that the factor of fouling is equal to 0.875. So from the relations now, that is Q is equal to, we can take it as here M into H, temperature difference multiplied by the area now. From this data, we can determine the area is equal to 128.2 now. Here problem number 4. A cross-flow heat exchanger with both the fluids unmixed is used to heat water flowing at the rate of 20 kg per second from 25 degrees centigrade to 75 degrees centigrade using gases available at 300 degrees centigrade to be cooled to 180 degrees centigrade. The overall heat transfer coefficient has a value of 95 watts per meter square per degree Kelvin. Determine the area required. For gas, Cp equal to 1005 joules per kg per degree Kelvin. The solution is given. The properties of gas can be taken as equal to that of air now. Heat transfer coefficient is equal to, heat transfer rate is equal to, that is amount of heat energy that is transferred per unit time is given by, here Q is equal to M into, here C into change in temperature. That is here 20 is representing the flow rate is given, the 20. Here H is equal to is given 4180 is given. Here into 75 minus 75 is the inlet temperature, outlet temperature 25 degrees is given, which is equal to 4.18 into 10 to the power of 6 watts now. So LMTD for the counterflow is equal to the temperature at the inlet is given, here 300 it is given now, minus of 75, minus at outlet is given 180 minus 25 divided by log of delta T I, that is 300 minus 75 divided by 180 minus 25, which is equal to 187.831 degree centigrade. For the correction factor now, F is equal to, generally it is applicable in designing of heat exchangers. Here P is equal to given T2 minus T1 divided by T1 minus T2, T1 minus T1. Here which is equal to 75 minus 25 divided by 300 minus 25, which is equal to 0.18218. Similarly, R is equal to 300 minus 180 divided by 75 minus 25. From this relation we got to 120 divided by 50, which is equal to 2.24 now. Okay, from this chart we will find for the oil at the given temperature, F is equal to 0.97. Hence, area is equal to, by using the relationship, that is Q is equal to A into H into delta T. By using the relationship, we got delta T into here M LMTD, mean temperature. By substituting just A is equal to, we got Q divided by here H into delta T to the power M. So on substituting this values, we got from this relationship, A is equal to, we got 241.5 meter square now. The flow rate is equal to, Q is equal to, on substituting the values, 4.18 into 10 to the power of 6 divided by 1005 into the temperature difference of 300 minus 180, which is equal to 34.66 kgs, that is required for the fuel which is having low temperature. Here problem number 5. In a food processing plant, a brine solution is heated from minus 10 degrees centigrade to minus 5 degrees centigrade. In a double pipe parallel flow heat exchanger, by water is entering at 35 degrees centigrade and leaving at 20.5 degrees centigrade at the rate of 9 kg per minute. Determine the heat exchanger area for an overall heat transfer coefficient of 860 watts per meter square per degree Kelvin. For water, Cp is equal to 4.186 into 10 to the power of 3 joules per kg per degree Kelvin. Okay, the given that in the problem is the cold fluid inlet temperature, that is the brine solution, is given minus 10 degree centigrade. Now, the cold fluid outlet temperature, because after extracting heat from the hot fluid, the temperature increases to minus of 5 degrees centigrade. Hot fluid at the inlet temperature, that the water is given 35 degrees centigrade. At hot fluid outlet is given 20.5 degrees centigrade. Heat transfer is equal to, we can take it as mCp into delta T, that is the amount of heat transfer from the hot fluid, is given by here 10 into 4.16 Cp is equal to 10 to the power of 3, here 30 minus 20.5. From this relationship we got 439.530 into 10 to the power of 3 joules per minute now. So multiply by 60, this we will get per seconds. So this value is equal to 7325.5 joules per second. The log mean temperature difference, logarithmic mean temperature difference Tm is equal to, is given the temperature difference at the inlet to the temperature difference to the outlet is required. That is here T1 minus T2 divided by log A T1 by T2 is given. So T1 is equal to the temperature at the this inlet is given which is equal to 30 minus of minus 10 now, because the inlet is given here 30 degrees is the water is given, but the inlet temperature of the brine solution is minus 10. The difference is nothing but equal to 40 degree centigrade. T2 is equal to the temperature at outlet is given, that is 20.5 is the outlet temperature of the water, and minus 5 is representing the brine solution temperature. So minus of minus 5, it is equal to 25.5 degrees centigrade. The subscripts H and C is representing the hot and cold fluids respectively in the given problems. So Tm is equal to, you can take logarithmic mean temperature difference is equal to 40 minus 25.5, that is delta theta 1 minus theta 2. Theta 1 is nothing but the temperature at the inlet minus temperature difference at the outlet divided by log of here temperature difference at inlet divided by temperature difference at the outlet now. So by substituting these values in this equation, we got this value is equal to 74.161 degree centigrade. Heat exchange is equal to Q is equal to UATM theta m, where U is stand for the overall heat transfer coefficient, A is the area of surface area, Tm is representing the logarithmic mean temperature difference, which is already measured, which is equal to 74.161 degree centigrade. The heating surface area is equal to, from this relation we got, A is equal to Q divided by UTM, which is equal to 7,325.5 divided by here U is equal to 860, Tm is equal to 74.161 degree centigrade. From this relation we got, which is equal to 0.211485 meter square now. This is the heating surface required for the exchanging the heat in a exchangers now. Here problem number 6 now. A tablet heat exchanger is to be designed for cooling oil from a temperature of 80 degrees centigrade to 30 degrees centigrade by large of stagnant water, which may be assumed to be remain constant at temperature of 20 degrees centigrade. The heat transfer surface consists of 30 meters long straight line tube of 20 mm inside diameter. The oil specific heat is 2.5 kilojoules per kg and specific gravity is equal to 0.8. Flows through the cylindrical tube with an average velocity of 50 centimeters per second. Calculate the overall heat transfer coefficient for the oil cooler. The mass rate of flow of oil, that is the R2 fluid through the heat transfer tube, is given by MH is equal to V into A into rho now. From this relationship we got to 0.5 into area is equal to 5 by 4 into 0.02 whole square. The density of the fluid is given 0.8 into 1000. From this relation we got to 0.1256 kg per second. And energy balance on the hot fluid then gives the total energy transferred. So Q is equal to, that is the energy transfer from hot fluid is equal to, Q is equal to MHCH minus TH1 minus TH2, where MH is representing the mass of the hot fluid and CH is representing specific heat of hot fluid. TH1 is representing the temperature of hot fluid at the inlet of the exchangers, and the TH is representing the outlet. And substituting the values in this equations we got, MH is equal to 0.1256 into CH is equal to 2.5, TH1 minus TH2, that is hot temperature is 80 degrees centigrade and it is reduced to 30 degrees centigrade, that is 80 minus 30, which is equal to 15.7 kilojoules per second. The energy transferred is given by the equations now. That is Q is equal to UA TM, where U is equal to overall heat transfer coefficient, A is equal to area of the cross section, Tm is representing the logarithmic mean temperature difference, which is equal to UA into Ti minus T1 minus T2 divided by log of T1 divided by T2 now. Since the temperature of one of the fluids remains constant during the flow passage, here it is immediately whether the calculations are made for parallel flow or counter flow arrangements. Both the arrangements would give the same values for log mean temperature difference and heating surface area for the specified load. Hence, not required to just analyze the same problem for parallel flow heat exchangers or counter flow. The results these are the same now. Hence, here T1 is equal to, we are having the temperature of hot fluid to the cold fluid at the inlet, which is equal to 80 minus of minus 20, which is equal to here now 60 degree centigrade now. And the temperature at the cold is given by, it is equal to 30 minus 20 is given now, which is equal to 10 degree centigrade. Tm is equal to, and substitute the values A into T1 minus T2 divided by log of T1 divided by theta 1 divided by theta 2, and substitute the values 60 minus 10 divided by log of 60 by 10, which is equal to 27.90 degree centigrade now. The surface area generally is given by for the pipe is equal to perimeter multiplied by the length, which is equal to pi d into L now. Pi d is equal to diameter of the pipe is equal to 0.02, where L is equal to length of the pipe is equal to 30 meters, which is equal to 1.884 meter square now. The overall heat transfer coefficient for the cooler is given by U is equal to Q divided by A into theta m now, where U is equal to overall heat transfer coefficient, Q is equal to the amount of heat energy that is extracted from the hot fluid divided by A is equal to surface area. Theta m is representing the logarithmic mean temperature difference. The substituting these values in this equation, we got 15.7 divided by 1.88 into 27.90. Doing the calculation, we got U is equal to 0.2987 kilojoules per meter square per second per degree centigrade. Okay, these are some of the important problems we discussed based on the heat transfer which is taking place in heat exchangers when the fluid is flowing in parallel or counter flow now. Okay, these are the textbooks referred for collecting these materials. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.